Hello everyone, and thank you for joining us for this webinar. We are excited to bring you this overview webinar on ETAP 22, an integrated and continuous intelligence digital twin solution that's driving sustainability through design, automation, operation, and optimization of electrical power systems. ETAP 22 offers an impressive set of enhanced power analysis modules, new safety capabilities, digital transformation solutions with advanced renewable energy modeling and simulation, leading-edge co-simulation technology, and model-driven real-time network management systems. This major release includes new solutions and features, plus thousands of enhancements and time-saving improvements. Through this webinar, and of course given our limited time, we will showcase key improvements. We will help you understand what's new in ETAP 22 and the benefits of upgrading to this version for your team and your customers. So let's go ahead and get started. ETAP Digital Twin is a unified engineering and real-time platform used to model, design, visualize, analyze, predict, control, and provide insight into the management and performance of electrical power systems. ETAP's unique and innovative digital twin solutions provide a single foundation and a database with seamless design to operation capabilities, real-time predictive simulations for situational awareness, and intelligence for operators and management. We also provide integrated applications for designers, planners, engineers, operators, and maintenance personnel. The ETAP Digital Twin goes beyond an integrated engineering analysis tool and provides an active blueprint of the electrical system, and offers an automated, rule-based design, model-driven predictive analysis, co-simulation platform, operator training simulation hub, combined with real-time analytics, asset performance monitoring, intelligent controls, and so much more. Harnessing the power of ETAP's ecosystem throughout the digital transformation process helps engineers, operators, and managers increase their awareness and understanding of their electrical systems in a cost-effective and repeatable environment. We continue to improve this transformation journey through ETAP 22. We are supporting our customers in this release through technology and best practices to design and operate power systems safely, reliably, efficiently, maintain compliance, and of course, drive sustainability. So here we go into the new features and capabilities of ETAP 22. A solid foundation is critical for any application, and ETAP 22 is no exception. We have improved compatibility and security compliances throughout the infrastructure. You will find the applications and the foundation to be more responsive and have performance improvements throughout. We've also improved the hardening and protection of application security in especially our cloud and mobile offerings. We continue to improve our high-resolution display support for many of our applications and interfaces. We are now supporting Windows Desktop 10 and 11, and we have removed support for Windows 8 and prior operating systems to maintain security and compatibility with cybersecurity requirements for our customers. And in that spirit, we've also platformed on SQL 2019, and we have significantly made replacements of SQL Compact Edition with SQLite as our primary database for reporting and other applications. So let's talk a little bit more about the ETAP application and its look and feel. We've changed the look and feel of ETAP 22 by giving it a new equipment toolbox, as well as enhancing the equipment editors. So let's see these in action. You will find the equipment toolbox on the right-hand side when you launch any project within ETAP 22. You can simply right-click and expand all the categories to see the individual components. If you have a larger monitor, you can simply go to the icon size and increase the size of the icons such that it fits appropriately within your screen. You can also drag and drop these icons or symbols to build your one-line diagram as usual. If you're looking for an icon or a symbol that you're not familiar with, you can simply do two things. You can turn on the search box and simply type in a portion of the icon name or component name that you're looking for. In this case, I'm looking for transformer, so I type in TRA, and ETAP immediately narrows down all the components that have the words TRA included in it. And again, you can simply drag and drop and build your one-line diagram. You can press X to exit out and get your complete list back. Or you can simply right-click and go to a list view and then scroll through the list and find the component that you're looking for. So once again, if you're looking for a power grid, you can simply drag and drop the power grid symbol into your diagram. We've also enhanced, as I mentioned, the component editors. So you can simply double click on any device which launches the property editor. And what you will notice in ETAP 22 is that the tabs have been replaced with a more compact and elegant list view on the left-hand side, allowing you to navigate within the component editor in a more precise manner. And these changes have been made to all the symbols or components regardless of their type, whether it's AC or DC elements. ETAP 22 also includes significant enhancements to the Intelligent One-Line Diagram, or ISLD. The Intelligent One-Line Diagram is the foundation for network visualization of electrical networks. The very first significant enhancement includes result animation. So let's see this feature in action. Within ETAP 22, you can simply go to one of the calculation analyses, run the simulation, and you can see, of course, the results directly on the single line diagram. And to enable or disable the flow animation, you can simply click on the button on the toolbar that allows you to see the actual flow shown as an animation going through the source or from the source all the way to the components. In this case, we're actually seeing amps, so we can see the amp flow from this wind turbine and from this generator going to the loads. And the spinning or rotating machines like the wind turbine generators, as well as the synchronous machines, induction machines, are also animated within this particular mode. So this is a really great feature that allows you to quickly visualize your network diagram, especially in a learning environment. The very next feature that we've added in ISLD is a major enhancement, which is what we call autocomplete. Autocomplete takes the effort of building the single line diagram through conventional methods of dragging and dropping and makes it much simpler. So let's see what happens when we build a simple one-line diagram with autocomplete feature activated. You can simply drag and drop your component as usual, and when you go to the connecting pin, ETAP gives you an intelligent choice in terms of which component you should pick next. And these choices are made based on electrical rules and certain intelligence that we've put into ETAP. As soon as you pick the very next component, ETAP automatically connects that component, auto spaces it for you, and gives you the choice for the next one. So we can connect our bus, we can essentially connect the very next device that we would like, which is let's say a circuit breaker, and we can continue building this one-line diagram with a piece of equipment. And before you know it, you essentially have your one-line diagram built based on intelligent choices and recommendations provided by ETAP. And that is autocomplete. The very next time-saving feature that we've added to the ETAP application is the Network Manager. The Network Manager allows you to visualize information across the entire single line diagram in a single table, allowing you to query as well as sort and find things very quickly within the diagram itself. So let's see the Network Manager in action. We can bring up the Network Manager in ETAP 22 from the System Manager on the left-hand side. The System Manager gives us a hierarchical tree of the one-line diagram components within the distribution or GIS view, multi-dimensional database, as well as rules and libraries. We can simply right-click on any component of our choice and bring up the Network Manager. So we can go ahead and look at our generators, we can look at our circuit breakers, and we can also look at buses and other large quantity components within the system. We essentially get tabs on the bottom, allowing you to switch between different categories. And you can simply take one of these categories, undock them, and expand to essentially see more details. And within the network manager, we have many other choices, including what columns to show or hide, grid options that allow us to essentially color code different aspects of the network manager itself, such as the coloring, as well as the font style that we are utilizing for the network manager grid itself. So here we can see that we've color coded the grid and increased the size of the font. You can also choose which columns you want to show and hide from the column chooser. And then most importantly, you can also do a find of different components in the system. We can simply select a particular bus in the network, click on zoom to selection, and the network manager will show you exactly where that component resides. You can also go to the advanced queries within the network manager. And within the advanced queries, you can pick the query that you would like. You can put the parameter and the value that you would like to compare it against. Verify the query that it is valid and execute to essentially exactly find the component based on the criteria that you're looking for. So an example could be finding buses less than a certain voltage. Another criteria could be finding all the single phase components in the system, or it could be as basic as finding relays or fuses in the system that don't have any library associated with them. So there's endless uses of the query within the network manager, and you can also use other advanced capabilities such as select all, clear selection, and also switching the selection. So when you select a number of components, you can alternately switch the selection to select everything else other than what you had previously selected within the grid. And once you're done with the network manager, you can simply dock it back into position and continue to utilizing it for other components as well. Let's take a look at the next two capabilities very quickly, which is flexible equipment symbol resizing and enhanced composite networks. ETAP traditionally has 5 different sizes for the components, size 1 through 5. In ETAP 22, you can take certain components and increase their size beyond those 5 stipulated limits. And they can be done by using the plus and minus sign on the keyboard. And this allows you to essentially specify certain components with much larger size based on their size or any other criteria that you choose. You can essentially do this with the wind turbine generator, synchronous generators, synchronous motors, and many more. ETAP 22 also allows you to easily open and close the breakers using a pop-up or a tooltip. Simply wait for the tooltip to pop up on a circuit breaker or switching device, and ETAP will essentially give you a pop-up allowing you to click and simply open or close that particular component, eliminating the need to right-click or double-click to open the editor. Again, giving you a time-saving feature for basic operations that you normally perform with the one-line diagram. You can also change the shape of the composite network from a rectangular to a circular shape. And this allows you to essentially show variation between different types of composite networks representing main or sub-main composite networks or substations. The efficiency gains and the improvements in the single line diagram don't just end there. We've added 2 more enhancements in ETAP single line diagram related to composite networks. Composite networks by definition allow you to layer or nest your one line diagram such that you can have a medium or high voltage layer and a composite network or a nested network allowing you to hold or contain the low voltage layer. These are graphically different layers of the diagram saved within the same database, allowing you to have a clean and precise or crisp view of your electrical one-line diagram. In ETAP 22, you can simply now take a portion of the diagram, right-click, and tell the program to convert it into a composite network. And in a single click, you can return the diagram back into its original position on the main single line diagram. So let's see this particular feature in action. We can simply find our main diagram go inside a composite network, so we are essentially one layer deep within the diagram, we can select a portion of the system. And before we do that, let's go ahead and run a power flow calculation so we can see what the flow results are. And we have 85.9 amps. We can simply right click, tell the program to convert this to a composite network, and we can go back and run our power flow once more, and we can see it's exactly the same flow again. When you go inside this composite network number 2, you can essentially see this is the portion of the diagram that we put inside our composite network. To bring this diagram back, you can simply right click and expand or unhide this diagram. The diagram comes back grouped with remote connectors, which you can simply select and delete. Once that is done, you can run our load flow again, and you can see the flow remains exactly the same. It's 85.9. So using a single right click, you can convert any portion of the diagram into a composite network with single or multiple pins and bring the diagram back into its original condition. The next capability that we've added is the ability to hide and show elements. Let's take the same section of the diagram that we were previously using, which has a flow of 85.9 amps. The use case is plain and simple. We want to hide the details in this particular diagram and only show the substation values. So we can simply take, once again, our diagram and hide this portion of the diagram. The flow remains the same. You can see a indication point letting us know that there's more details associated with this circuit breaker, but we have simplified the diagram to only show what is the flow going into this section of the system. To bring it back, you can simply expand or unhide and bring your diagram back. ETAP 22 also includes a new digital twin element for modeling of electrical networks, which is the active harmonic filter. Active harmonic filter essentially allows us to do two things. One is correct the unbalance in the system, as well as power factor correction, and it also allows us to filter out harmonics in an automatic or manual manner. Let's just take a look at active harmonic filter as it's operating for balancing or correcting the unbalance in the network. We have our active filter component that we can double click, bring up its various properties, and essentially connect it as a shunt component within the one-line diagram. When you run an unbalanced power flow, we can see the per phase flow, ABC flow, and we can clearly see there is unbalance on cable 2 as well as the transmission line. The active filter is currently turned off. We can simply go in, turn on the power factor and load balancing mode, and rerun the power flow again. And essentially ETAP will use the active filter, inject the ABC current flows such that cable 2 is balanced as close as possible. And this is being done with respect to the overall rating of the active filter. Once the rating limit of the filter is met, there's no more unbalanced correction possible. So you can essentially use this new element to go ahead and look at your distribution system and use active filters to compensate unbalance or power factor correction as needed. ETAP 22 also includes digital twin elements for modeling network protection. One of the changes done for modeling the network protection is improvements to the high voltage or medium voltage circuit breaker library. The library now complies with IEC IEEE 62271, which is the standard for high voltage switchgear and control gear for alternating current generator circuit breakers. You can essentially choose from ANSI, traditional IEC, as well as IEC IEEE within the circuit breaker library and pick the manufacturer and model of your choice and use it within the simulation. The quick pick for the circuit breakers has also been improved, including a quick pick with sorting and filtering capabilities, allowing you to quickly find the manufacturer, model, or a circuit breaker based on its size or rating very quickly and efficiently. There are similar standard improvements also for low voltage circuit breaker. We've not only expanded the short circuit ratings for the low voltage breakers, but we've done so by adding the slash rating for LV and C molded case breakers and individual pole interrupting rating for ANSI and IEC low voltage breakers. We're also showing ZSI availability in the LV breaker quick pick, allowing you to identify whether a particular circuit breaker is capable of zone selective interlock or not. One of the most important features in ETAP are the use of intelligent controllers. The intelligent controllers allow you to dynamically model equipment controllers such as primary, secondary, and tertiary controllers that are needed not only for renewable energy control systems, but conventional systems as well. These ready-to-use controllers with user-defined parameterizations are available for wind turbines, solar inverters, energy storage inverters, and STATCOMs, but they're also available for secondary control systems such as a hybrid power plant controller or station controller, as well as a microgrid controller. For energy storage, you can use grid following and grid forming inverters, and you can also use grid code analyzer for renewable energy control system analyses. These controllers can also be used as a foundation for the ETAP OTS or Operator Training Simulator. So let's take a look at some of these controllers in action. The controllers can be dragged and dropped from the system toolbox. You can double click and open the controller to see which devices you are monitoring or controlling and adjust them. You can also pick what DLL is being used for this particular controller. A DLL stands for Dynamic Link Library, and it's essentially the black box implementation of the control system. In this example, I have picked the microgrid controller, and you can see the user-defined parameterization on the bottom left corner. Each of these functions defined within the DLL has the ability to adjust its parameterization, such as values, and enable and disable for certain functions. Many controllers can be put together within the same network, and they can be nested together or layered together to interact in a coordinated manner. We can simply put our controllers in place, set about the parameterization, bring up our plot views, and run the simulation. And as these controllers take various effect within the system to control the wind, solar, energy storage, adjust them based on the loads, and dispatch synchronous machines in the system, you can see the response and behavior on our dynamic live plot views. And the plot views are essentially telling us we had a brief disconnection from the system, and we're black starting this network back again using our energy storage, PV, wind, and our synchronous generator such that we can serve the load within the network. Use these controllers within your existing systems or greenfield systems to truly bring in a closed loop control within your simulation, and use these control systems to parameterize and download the parameterization directly to the ETAP hardwares for microgrid and PPC. These controllers in general help you save time, energy, as well as de-risk the project, allowing you to go all the way from design to operations within a known and simulated and controlled environment. ETAP 22 also includes updated, verified, and validated equipment libraries. We've added more than 5,000 protected device models with respect to low voltage breakers, trip units, fuses, and relays, and more than 4,000 solar panels and cable models have also been added into ETAP, making this the most comprehensive equipment library available for power system analysis. And of course, since these libraries are verified and validated based on our nuclear QA, you can be rest assured that the component data that is being utilized for your digital twin is valid, accurate, and up to date. Cable systems have also been improved by allowing us to have protective and neutral conductor sizing based on tables for BS 7671, IEC 364, and NFC 100. Cable model forms are also now available based on 7671 2018 standard A2 2022. We've also added new conduit types and enhanced the annotations for underground raceway systems. In the ETAP underground raceway system, you can see the new conduit types in our drop-down list for the conduit type selection. And you can also see the new annotations available to us for example, the steam pipe, giving us the temperature of 80 degrees Celsius. And of course, you can also see the annotations for the center to center spacing as well as the edge to edge spacing that's available for the underground raceway system. You can also calculate the energy capability within the cable editor, which is the K square S square for each phase, neutral, and protective earth conductor. And you can also compute the maximum possible energy based on the short circuit conditions and the protective device settings within the same cable editor as well. ETAP 22 also has significant improvements to AC arc flash. AC arc flash allows us to reduce risk, improve safety, and enforce compliance. And you can do so now based on international standards. You can evaluate arc flash and arc fault based on IEC 60909. That includes the arc flash decay as well as single phase arc flash calculations. And you can also run arc flash simulations based on DGUV or the German arc flash standard. These options are essentially available in the arc flash study case for you to choose between different methods. We've also expanded our shock risk assessment list based on regional electrical worker safety standards. Standards that are traditionally included within ETAP were NFPA as well as IEC standards, but we've also expanded them to include Canada, Mexico, Brazil, Russia, China, and so many more. And we will continue to expand the shock risk assessment safety standards in subsequent releases. Another new capability that we've added to our safety portfolio is lightning risk assessment. Lightning risk assessment allows us to raise the protection from lightning exposure into new heights. And we can do so by identifying and assessing the risk for a given structure due to lightning flashes or lightning incidents that may happen around that area. The lightning risk assessment calculator allows us to comply with standards for lightning protection systems such as NFPA 780, 2014 and 2022 standards, as well as IEC 62305 edition 2, which gives us the ability to define protection against lightning and do certain risk management. The lightning risk assessment calculator also includes a lightning density and frequency map. Let's take a look at the lightning risk assessment in action very quickly, and there will be a subsequent webinar on this feature alone. We can bring up our lightning risk assessment calculator and build our main structure. We can simply press add, build the structure that we would like, close the shape, and give this structure a certain height. Once the structure is completed, we are essentially ready to look at the risk evaluation warnings. And according to NFPA 780, a lightning protection system is optional in this particular case with a lightning flash density of 1 flash per kilometer square per year. We can of course go to our lightning frequency map. We can pick from a different lightning density such as 12 flashes, which is updated within our calculator. Go back to our simulation and you can see the protection system is still optional. However, this is a case where the trees are with a height greater than a structure height. If there are no other objects around this particular structure, such as trees, the risk evaluation is automatically adjusted, and it is now recommended that a lightning protection system be installed. So this is a very quick example of the lightning risk assessment calculator, which you can see in a subsequent webinar in more detail. ArcFlash also includes a new capability, which is Label Maker. The Label Maker allows you to generate and customize AC and DC ArcFlash labels directly within ETAP itself without utilizing Microsoft Word or any other application. This is a graphical tool that allows you to not only create the labels but also save those labels as a template, and you can create any modern ArcFlash label using this particular application. You can include or bury QR codes, and you can also localize these labels based on your local language. And with the design view, there are many different properties available to you to essentially change the look and feel of these labels based on your company standards. You can simply run your ArcFlash analysis within ETAP, pick the template of your choice, and ETAP will automatically populate the data within the label maker based on the analysis results and using the template of your choice, and you're ready to print these labels on your preferred printer, making the entire process of ArcFlash analysis very quick and efficient in ETAP 22. We have also improved our ArcFlash calculators, including instant result visualization. The DC ArcFlash calculator includes generation categories and the behavior of single and double diode IV and PV curves for solar panels. And the German ArcFlash calculator also has improvements in its iterative method as well as the worst case method. And we've added the arc elongation effect specifically for PV systems as well. As the arc is burning in the system, it consumes the material, causes the arc to essentially elongate or stretch, and once it has stretched to a certain threshold point, the arc can actually self-extinguish before, in certain cases, a protected device may operate. And this arc elongation effect is now available within the calculators. The industry-leading power flow analysis solution, which is ETAP unbalanced load flow, has also been enhanced. We've added the ability to auto-run the calculations similar to the balanced load flow simulation, and the plot analyzer can now be used for single-phase system equipment plotting as well. We can go to the unbalanced load flow mode, run the simulation, go to our plot analyzer and pick a three-phase and single-phase bus. Look at the voltage phasors in a combination, and what ETAP gives us is a very clear indication or a clear picture showing us the phasors as expected for the main bus, which is relatively balanced, and our single-phase vector, which is magnitude and angle for the single-phase bus. And of course, with the plot analyzer, you can individually turn on or off any of these values, especially if you have a number of them plotted at the same time. Time domain load flow has also been improved significantly in ETAP 22. Time domain load flow itself allows you to automatically and sequentially vary the load and generation and solve the steady state power flows or a function of time. And the time can be a matter of minutes, hours, days, weeks, months, years, or multiple years. Time domain load flow essentially includes the ability to perform a quasi-dynamic load flow as well. This quasi-dynamic load flow can include the controller dynamics within the simulation, allowing you to essentially control or understand the time domain simulation from one step to another. So the steady state power flows essentially have a closed loop behavior or closed loop control behavior using the controller dynamics within the simulation. You can also plot the graphical results now for static var compensator, StatComs, VFDs, induction, and synchronous motors. And we've also expanded the AC-DC element plot parameters. One of the other things that you can do in time domain power flow now is consider millisecond timescale instead of purely seconds. And we've also added the ability to include user-defined Python reports. So you can create your own report and your own plot depending upon your need or requirements from this particular simulation. Time domain load flow is invaluable when you're performing renewable energy simulations over a period of time with microgrid controllers and or power plant controllers within the same network. Time domain load flow has other applications as well, such as ports, aircraft, or any other system that has variation in a continuous manner between load and generation, and that variation needs to be analyzed over a period of time, including distribution system planning as well as railway power system networks. One of the most significant improvements in ETAP 22 is the addition of a new module, which is unbalanced short circuit. Unbalanced short circuit allows you to do a device duty calculation and evaluation for single phase, multi-phase AC and DC systems. With unbalanced short circuit, not only do you apply an unbalanced fault on an electrical system, but you're applying an unbalanced fault on an unsymmetrical system. These unbalanced faults can include shunt faults, line to ground faults, line to ground, as well as simultaneous faults. The unbalanced fault on unsymmetrical systems, especially line to ground, can be applied from phase A, phase B, or phase C to ground, because each phase, based on the nature of unsymmetrical system, can be completely unbalanced. So let's see this unbalanced short circuit module very quickly in action. We can simply switch over to our unbalanced short circuit mode and run our simulation. And in this case, I'm running a simple device duty simulation, and we can see for a combination of a three-phase as well as single-phase system, we can see the individual A, B, and C phase currents and angles, as well as the contribution from the downstream components. You can simply right-click and place a fault and rerun the simulation, making it a very easy to use program, similar to the balanced short circuit module. You can pick any bus, whether it's three-phase or single phase, and perform this kind of calculation. In this case, you will see that there was no contribution from load 2 because this is a static load or not a constant power load. But we can see lump 2 is actually a combination of a constant Z and a constant power load, and therefore there is actually some contribution from this piece of equipment. Inside the study case, you can choose between the AC modeling, DC modeling. You can also set up options for your pre-fault loading right before the fault inception. Select which buses are included for shunt faults, and of course which buses are to be included for simultaneous faults. And ETAP, using this unbalanced short circuit, can allow you to include faults on not just transmission systems or industrial systems, but as well as low voltage networks such as renewable, airports, data centers, and so many more. Unbalanced short circuit, therefore, is the ultimate short circuit module that you would need for any type of system that is the most comprehensive in terms of AC and DC modeling within a single application. The standards that are supported by unbalanced short circuit include GOST Russian standard for AC systems, ANSI C37 also for AC systems, 60909 for AC systems, and IEC 61660, which is meant for DC systems. You can have, of course, the result visualization on the single line diagram as well as the geospatial diagram, and the generator circuit breaker duty evaluation is also included per IEC 62271. In order to evaluate our DC short circuit, we can just simply run our DC scenario here, and you can see the short circuit simulation on the DC network, which is shown in blue, based on IEC 61660. And we can see the contribution, which is the forward current and the return current in our DC network, along with the phase contribution values and the voltages as well. ETAP also provides the evaluation of the AC and DC short circuit using the alert view. And once again, similar to load flow or balanced short circuit, you can see the critical and marginal alerts within this alert view. Simply double click on the component of your choice, and ETAP will of course highlight and select and show you where that device is, and you can continue making improvements and dimensioning changes within your electrical system. Harmonic analysis in ETAP 22 also includes major improvements. Harmonic analysis is used for a comprehensive load flow and frequency scan of your electrical system that may have power electronics or any other nonlinear devices that generate harmonic spectrum. The harmonic analysis now includes the ability to give you total and displacement power factor, transformer derating, which is considering the eddy current losses based on ANSI C57, zero sequence harmonic frequency scan, and updated rule books with limits for harmonic current emission that's used to alert or inform you that you are exceeding these limits at the point of interconnection. And these new rules have been added based on Australian standard 61000 as well as ENA G55 2020, which is the emission limit for United Kingdom. So let's see a few of these in action within ETAP. The harmonic analysis zero sequence scan is selected from the study case, so you can choose between the existing positive sequence or switch over to the zero sequence network and run the frequency scan. And as usual, ETAP will show you the impedance at the one line diagram level. You can use the slider to navigate through and see the zero sequence impedance changes, or you can simply go into the plot view and see the frequency scan information for any number of buses, including the positive and zero sequence frequency scan. You can also run the harmonic load flow within ETAP, and the program essentially now gives you the current, total harmonic distortion, as well as the total power factor. The study report gives you the displacement power factor, which is the power factor in the system without harmonics, and the total power factor is giving us the power factor based on harmonic content within the electrical system. So this is the true power factor that we will be observing at the point of interconnection. You can also change the rules for harmonic emission limits by going into the harmonic page, and instead of using the global compliance rules, you can also use the local compliance rules. And these rules are based on ANSI 519 and the new AS-NZS 61000 or ENA G55, which is the British Harmonic Compatibility Limits. And of course, you have the IEC 61000 as well. So you can pick from these different emission rules and use those within the program such that we can essentially get an assessment of the harmonic limits that are being generated in the system and compare them versus these rules. And any issues or violations based on these rules are then, of course, graphically shown in the ETAP program in the alert view. And the alert view essentially is a very good way to let us know that we are exceeding the total harmonic distortion or the individual harmonic distortion or both within this electrical system. The harmonics analysis module also includes flicker meter. Flicker meter allows you to import contraid files in CSV format and analyze up to 20 different signals at any given point in time. And the purpose for analyzing these signals is to evaluate the flicker compliance against emission limits. The flicker calculations are based on IEC 61000-4-15, which is the standard for electromagnetic compatibility, and the calculation gives us instantaneous, short-term index or PST, and long-term flicker index or PLT based on a voltage waveform that's entered into the calculator. And the purpose is to essentially determine the level of flicker in the voltage waveform based on various starting and stopping actions of equipment within a system, such as induction machines. We can launch the flicker meter, open up a CSV file, and the program very quickly loads that file into the plot so that we can actually zoom in and see the details of this particular waveform. You can use the control key and right click to essentially continue zooming into this diagram, and you can see our waveform emerging from all these data points that were read into the program very quickly and swiftly. You can see in the magnitude in the envelope here, there's a slight variation in voltage, and this is the whole purpose of the flicker meter, is to look at all these variations in magnitude in the given waveform and compute or calculate the short-term and long-term flicker index. Let's go ahead and compute the short-term index and see our result. Once the calculation finishes, you can see a simple Excel output that shows us the file name, the nominal voltage, frequency, and the sampling frequency, and how long was that data file. And you can see this data file was only 600 seconds, so not long enough to compute the long-term index, but long enough to compute the short-term index. And we can see for the voltage magnitude for phase A, the short-term index is 0.97. And then of course this can be evaluated against the emission limits to determine whether we have good power quality within this network or not. ETAP 22 also allows you to conform to grid codes and maintain compliance from design to operations to performance. The variable nature of renewable energy introduces many power quality concerns, including frequency and voltage control, that may negatively impact the reliable performance of a power system. Grid codes, interconnection, or evacuation criteria must be followed during the proposed system design and continue to maintain compliance under the grid-connected operation. The ETAP grid code solution is used for the design, analysis, protection, optimization, operation, and maintenance of renewable energy systems. The ETAP grid code in ETAP 22 utilizes a model-driven electrical digital twin with automated analysis, predictive calculations, network optimization, validation processes, and intelligent, secure hybrid power plant control to ensure local grid code or standard compliances are maintained throughout the power system design as well as operations lifecycle. In ETAP 22, you can automate the grid code assessment, including the real and reactive power capability evaluation. You can also perform harmonic distortion evaluation, transient voltage write-through, and consider capability curves for wind turbine generators and inverters. So let's see our automated grid code compliance in action. We can use our grid code analyzer within this particular electrical system that has PVs, energy storage, STATCOM, and wind turbines to essentially determine which devices are being monitored and controlled And of course, based on our grid code analyzer, we can also define specifics of the capability curve in this PQ and VQ capability in terms of the minimum sweep and the maximum sweep of voltage as well as power within the particular simulation. Once the simulation is completed, we can essentially look at the grid code analysis report and look at the chart for PQ capability at 95% voltage. And we can see that the reference PQ curve is overstepping the PQ capability that's computed for this particular facility. So this region where there is intersection or overlap is where we have non-compliance. Similarly, we can see the same PQ capability at 100% voltage as well as 105% voltage, and the VQ capability at 100% active power. And again, we can see that there is a non-compliance region in the bottom right corner. This is without a StatCom in place. And of course, the same simulation can be repeated with a StatCom, and we can see the change in results shortly. With the StatCom included, we can see that at 95% voltage, the StatCom is able to bring the non-compliance region back into compliance. So the reference chart is essentially within the PQ capability of this particular site. Same thing at 100% voltage, at 105% voltage, and finally at active power of 15% and an active power of 100%. We essentially can see that there is complete compliance using a StatCom within the system. So the grid code assessment lets you automate these sweeps of voltage and real power and determine whether you are within compliance within the given PQ capability limits, as well as low voltage and high voltage write-through limits provided by the grid at the point of connection. With grid code analysis and the automated assessment, it's the most important tool that you need in your toolbox in order for you to perform any grid interconnection studies from a steady state, transient, and harmonics perspective. One of the other components that are important to grid code compliance and stability are smart inverters. Smart inverters, including their modeling and simulation, have been enhanced in ETAP 22, allowing you to have more autonomous logic-driven decision making and the ability to simulate the impact of utilizing smart inverters to ensure the grid stability and reliability of your distributed energy resources. Smart inverters include multiple modes of operation and control, include volt-var, volt-watt, watt power factor controls, and many more options. Let's take a look at the smart inverter in ETAP 22. We can bring up the inverter property editor and switch the AC operation from any other control mode to smart inverter control. And once we are in the smart inverter control mode, you can specify the constraints of the smart inverter, including the cutoff voltages, specify the control modes, and for these particular control modes, you can also specify the Q or P base, including their priorities. And then, of course, if there is any type of control, you can specify the control curve based on user defined by adding your own points, or simply selected from the rule book, such as the 1547 inverter control curves for category A and category B smart inverters. And then immediately apply these within your distribution system or distributed power system and comply with distribution grid codes in a single click. You can therefore use the smart inverters to not only meet the requirements and compliances of your own region or per IEEE 1547 standard, but also meet California Rule 21 requirements as well. Star protection and selectivity allows you to gain insight into line protection, relay performance, and evaluate system-wide protected device operation. AutoStar, or Automated Coordination Evaluation, has been improved to allow you to do this evaluation beyond the minimum time. And all protected devices are now supporting user-defined fields. These user-defined fields allow you to extend each component, such as a relay, fuse, low voltage circuit breaker, and include parameters for those devices that are not commonly used in protection and selectivity. And by doing so, you minimize the risk and you close the gap when you go from design into commissioning that particular device. By including functions within the device during design phase that are not traditionally used in protection and selectivity, you are able to generate a complete report with a comparison of the user-defined fields, such that this report is given to the commissioning engineer and he can establish or set up that device comprehensively from a single source of truth. This avoids any errors made during commissioning and any subsequent unforeseen or forced outages that were created due to gaps between what was done during design and what was implemented during commissioning. Let's take a look at user-defined fields a little bit more in detail in ETAP 22. Each component, such as the protected device, has an asset or user-defined field. All your existing user-defined fields within ETAP have been converted into this easy to use and find table. It includes common user-defined fields as well as device-specific fields. And these common and device-specific fields are driven through a template. So let's open up our template very quickly and observe what happens with one of these devices. Let's take our low voltage circuit breaker, and we want to go ahead and add a new field, a new user-defined field, and we'll essentially call this last maintenance date. And this is a type of field which is a date. We can go ahead and also put in a helpline here, which is enter date this device was last main. We can also add a device specific field, and we can give it some generic name just to give it some kind of understanding with some numeric value that goes from 0 to a maximum of 500. We can add another one, which is a list box that can have a value of yes and no, and this could be something as simple as a thermal function, which is part of this particular breaker, but not necessarily used in any kind of simulation when it comes to protection or coordination. And then of course within this template editor, you can also go inside the data manager, and within the data manager you can see all the changes that exist for those components in base or revision. You can also go inside the report manager and export the user-defined fields, including the 2 new fields that we just added that are device specific. So we can open up our low voltage circuit breaker, go to the asset or user-defined fields, and we can see our last maintenance date, which is a date type field, as well as our device specific fields. And in this particular field, which was a numeric field, if you type in 900, it will reset itself to the maximum value that we had established of 500. And the thermal function could be a yes or no. And since we had only included yes, a blank would imply no, and you can easily select yes. And each of this data is then saved with this particular component using its common user-defined fields as well as its device-specific fields. So using these user-defined values, you can expand the capability of your protected devices to host complete set of data that is particularly useful or needed, not just during design, but also during commissioning, such that you have a single source of truth in one common database. And these fields or values also interact or integrate with eProtect, which is a centralized asset management system that you can use for not only low voltage breakers, but particularly for relays as well. Star also includes a brand new sequence of operation slider that allows you to essentially review the sequence of operation, especially for large and complex systems, in a very easy and convenient manner. Once you run the Star sequence of operation, you essentially get the sequence of operation event list. From this list, you can pick a particular component, and the program will essentially move the slider, letting you know at what time did that particular event happen, and this case happens to be at 5 seconds, and will also highlight and show you which device actually operated during that time frame. You can essentially pick another device. In this case, it happens to be circuit breaker 8, which is tripped by overcurrent relay number 7. And the program will flash and indicate and let you know in the sequence, this is the first device that essentially tripped in the network. You can essentially move and navigate through the entire sequence one by one. or you can simply turn on the automated sequence of operation where you can select up to n number of devices to flash, press play, and the program will essentially walk you through the sequence, such as numerically 1, 2, 3, and so on, making it very easy and convenient to analyze the entire diagram at one shot, or systematically focus or zero into the devices that you want to analyze in more detail. Star protection and selectivity also includes additional new enhancements and capabilities, such as the ability to consider or ignore maintenance switch in sequence of operation. Each device may have a maintenance switch on or off, and the new option in the study case allows you to globally enable or disable or consider or not consider the maintenance switch in the sequence of operation, saving you time and effort in your what-if simulations. The star view or the TCC has also been enhanced with additional visibility and display enhancements, including motor line and terminal acceleration curve, the ability to show minimum time areas, the ability to show or hide curves from the right-click menu, and the ability to find the minimum time differences in a normalized TCC. STAR-Z or the distance protection program has also been enhanced, allowing you to simulate protection impact based on unbalanced faults, such as A to ground, B to ground, and many more. STAR-Z also integrates with ETRACS for railway system protection simulation, allowing you to have an even more comprehensive railway traction simulation program. And it also includes improved line protection libraries with user-defined comparators, frequency option for operating and restraint signal list, and many more. You can also now create and manage star views or TCCs in STAR-Z mode, and you can also have normalized TCCs based on STAR-Z single fault report in ETAP 22. Reliability assessment allows you to assess the availability and the quality of power supply at each customer service entrance using single or double contingency methods. Reliability assessment in ETAP 22 has been enhanced with improved visualization through data blocks. We've also improved the plotting through the GIS diagram and expanded the equipment handling to include STATCOM, static var compensator, UPS, and of course wind turbine generators as part of your reliability assessment in the electrical system network. Switching optimization is particularly used to determine the optimal system configuration to achieve certain user-specified objectives, such as minimizing real reactive power losses or minimizing the amount of unbalance in a particular system. Switching optimization in ETAP 22 has been enhanced to include the alert and visual display on the ETAP one-line diagram and the GIS diagram as well. We can now include the modeling for switch capacitor banks in the power flow simulation and improved the feeder balancing and optimizing voltage objectives as well to be more precise and accurate. We have also included a new phase load balancing objective as part of the switching optimization module. Volt var optimization allows utility planners to minimize reactive power losses and of course improve overall grid planning through the use of edge devices for voltage and var support. This module has been enhanced to include alert visualization directly on the GIS diagram, and we've also enhanced the modeling of switch capacitor banks as well as distribution transformer tap changers. Switching sequence management allows the users to ensure safety by graphically building, simulating, and validating the switching sequence plans. Switching sequence management allows users to ensure safety by graphically building, simulating, and validating switching sequence plans. These validations of switch plans use unbalanced power flow, and now in ETAP 22, you can simulate switch plans on the one-line diagram or the GIS diagram as well. You can export these sequence plans to Microsoft Excel, or you can export the plans to an online sequence management viewer provided as part of the ETAP real-time solution. Therefore, you can use switching sequence management not only during system design, but also during operations and maintenance. Fault management and service restoration allows us to determine the optimal restoration strategy and recover the maximum number of affected customers during a forced or unplanned outage. Fault management and service restoration has improved objectives such as minimization of feeder overloads and optimizing the voltage profiles. And it also includes a new plot allowing us to plot voltage versus distance per phase. Transient stability accurately simulates power system dynamics and transients. And in ETAP 22, we've added new actions for transient stability, which include unbalanced faults such as line to ground, line to line, and line to ground for branches. For example, in transient stability, we can apply a three-phase fault on sub-3 bus and we can see the voltage goes to 0%. We can quickly go inside the study case, change this action to line to ground fault, and we can also include an additional fault impedance and click OK and rerun the simulation. And we can see the voltage essentially now is not at 0% voltage, but around 64% or so. And this behavior essentially is available for buses as well as branches in ETAP 22. In ETAP 22, you can also go to the utility and select between voltage impact ramp and frequency impact and ramp. And these options essentially allow you to simulate the impact of high voltage ride through or low voltage ride through, including frequency ride through capabilities by changing the behavior of the power grid and observing the response of the rest of the system with respect to the change in these actions. You can also go to the generator and select from new options, including generator impact, ramp, and voltage impact and ramp for synchronous machines as well. ETRAX is a solution for railway system simulation. It allows you to design, analyze, and maintain AC and DC railway infrastructure. The design and analysis of AC and DC railways has been improved by allowing the users to have multiple train type categories and speed limits. So you can define between a regular speed train, a high speed train, an intercity train, a freight train, and essentially have multiple train types and their speed limit categories defined within the corridor. You can also lock the track length in the geospatial view, and the speed limit error checks are also included for multiple train types. The electrical GIS is synchronized within ETAP, allowing you to visualize and analyze electrical information through the single line diagram as well as in a geospatial manner. This electrical GIS has been improved by including substation diagram as well as the ability to visualize relays and instrumentation synchronized with the intelligent single line diagram or ISLD. The ETAP API, which is a RESTful API for interoperability, uses a web services based architecture for ETAP to interact with other complementary applications through data messaging. We can connect to ETAP from any device or any platform, and these ETAP services are delivered over a REST API or a secure HTTPS connection using the data hub. This is also the core or the foundation that's implemented as a Python client in ETAP Py module. With ETAP API, you can run scenarios, run studies, get project data, all from within your favorite tools. The ETAP Python, or the scripting and study automation using Python, allows us to integrate ETAP with Python scripting language. You can run ETAP studies remotely and in parallel across machines, and this API has been expanded in ETAP 22 to include automation of switching optimization, unbalanced short circuit, as well as contingency analysis. And as always, the detailed reference documentation, including the descriptions and sample code that you can run on the fly, are available as well. The ETAP app is now on version 7, and we encourage you to go to the Google or Android store, iOS store, or Windows store to update your ETAP app as soon as it's released. In summary, ETAP 22 has thousands of new enhancements, features, and capabilities. We barely had time to scratch the surface and show you all the nice improvements, enhancements, time-saving features, efficiency improvements, and of course, accuracy in modeling and simulation that you would only come to expect from ETAP. And we can deep dive into many of these new features and capabilities in our upcoming webinar series. Thank you.